All right, hopefully it's working online now. Okay, awesome. Yeah, so this has been a great conference. Thanks very much for organizing it. Yeah, it's been great to hear all the talks so far. So what I want to talk to you today about is some of our work looking at charge correlations and charge density wave order in some new classes of kagome compounds. So Joe spoke a little bit about some of the motivations behind this yesterday, and I'll try and rehash a little bit of it today with a slightly different angle. So first off, just for anyone, maybe for the students who weren't here yesterday, so what is a kagome metal? And so kagome network is it's one of these 11 Archimedean lattices that you can use to tile two-dimensional space. It's this one down here in the bottom left. So it's basically just a network of corner sharing triangles. And it's a kind of a commonly shown like sort of geometric and mathematical motif, but it also is a lattice that forms in real materials rather readily, which is what makes it exciting, from a materials perspective, because one can actually try and explore a rather broad palette of materials to try and realize some of the more interesting states predicted in kagome metals. And so, the reason being is that if you look at intermetallic compounds, and the material scientists have known this for a while, that if you just think about hexagonal close packed balls, you put them in some AB stacking, and you just replace 1/3 of the balls with much bigger balls. And then just sterically, the way they want to pack is just some layer. They want to basically form a supercell that's alternating layers of a kagome network and triangular lattice. And so the way that those layers alternate along the z-axis forms a variety of very common intermetallic types. And so if you just look at this histogram of known intermetallic phases like the calcium copper 5 and the lavase phases, more or less some of the fundamental units which comprise those structures are kagome networks of metal ions. Okay, so why are kagome metals in particular interesting? So as Joe motivated yesterday, is the band structure at some simple tight binding level for a single orbital model. If you were to think about what the band structure looks like, you have a coexistence of three sort of interesting features. And so Joe mentioned a few of these yesterday. The first is where he focused was the flat band feature, right? So you have this hopping interference effect that localizes electrons, and you end up with a flat band. But if in the zone corners, you also end up with Dirac points, okay? And at the zone boundary edges, you end up with a series of two saddle points, okay? So if you just cut along high symmetry directions here, you can see here's the Dirac points at the so-called K point in the brilliant zone, and these two saddle points at the M points, and then the flat band feature. Okay, so this is interesting because one can potentially try and engineer electronic states that sort of kind of sample a little bit of topological and non-trivial types of electronic features, as well as correlation effects that can be engineered via either trying to increase the density of states by tuning the band filling to like the flat band, or potentially near these saddle points, which also form Van Hoff singularities. And so if you were to look at sort of the coexistence of these interesting band features across the literature in recent years, experimentally exploring these, there's been a lot of studies, for instance, looking at kagome metals, for instance, iron tin or terbium manganese 6 tin 6, where there's interesting sort of large anomalous Hall effects derived from the Dirac point in the compound. Basically, it gets gapped out via spin-orbit coupling. You have a large Berry curvature and a large anomalous Hall effect in those systems that are magnetically ordered. As Joe discussed yesterday, there's been a lot of experimental effort recently trying to tune band filling of kagome metals towards this flat band to bring it to the Fermi level, in which case, some recent results on nickel-3 indium, there's sort of a heavy fermion-like phase behavior that seems to start manifesting. But the focus of this talk is really trying to explore fillings near this other feature, near the saddle points in the brilliant zone. And so, these so-called Van Hoff points, there's examples where the filling seems to be close to that in the so-called 135 class of materials, or alkali metal, vanadium-3, antimony 5, and the so-called 166 class of vanadium-based compounds, which is a rare earth ion. And I'll talk about two examples of charge order or charge density wave states in each of these compounds in this talk, okay? Okay, so why is tuning the filling near a Van Hoff point interesting? First off is that, okay, you can have nesting between these points at the Fermi level. If you can tune the Fermi level to the Van Hoff point, you just have a series of points which can be connected by a well-defined wave vector, and so this can promote instabilities along this wave vector and create peaks, and for instance, the Linhard susceptibilities, for instance, in the real and imaginary components. And for kagome metals, there's two separate flavors of Van Hoff singularities, a so-called M-type or mixed-type Van Hoff singularity. And what that means is that the wave functions that comprise this, the states here at this point are derived from multiple sublattices in the kagome network. There's 3 sublattices in the kagome network, so these are coming from 2. And then there's a so-called P-type, which is a pure type Van Hoff singularity where the wave functions are derived from just a single sublattice in the kagome network. And so there's been a lot of theoretical work exploring kind of unusual physics that can happen if you can tune the filling towards this P-type Van Hoff singularity, okay? And there's a number of different interaction-driven instabilities, which range from various flavors of charge density wave order and unconventional superconductivity and bond density wave states. I'll call out 2 sort of the interesting predictions, one of which being, if you can imagine having a bond density wave order that modulates hopping across the kagome network, one can imagine a so-called flux phase, or as I'll call it, orbital antiferromagnetic phase, in which you realize antiferromagnetism in the absence of local spins. The second feature, which is predicted, is a so-called D plus ID superconductivity, which is a leading instability in a lot of kagome lattice Hubbard models. And both this flux phase and D plus ID superconductivity also map to some earlier work looking at Van Hoff instabilities driven by Van Hoff fillings in honeycomb networks. So this is kind of a broader realization of a lot of that work.
Sorry, Stephen, what is a bond density wave state?
So effectively, the electrons don't localize on the site anymore. When you have the charge density wave order, they're sort of localized on the bond. So, okay. So sometimes I get yelled at, sometimes we're using a charge density wave as an umbrella term, because some people say I'm supposed to call it a D density wave state or something else. So there's lots of opinions there. But I call it charge density wave state sort of an umbrella term, and it can either be site-centered or bond-centered. Okay. So just to highlight a little bit of terminology. So on the kagome lattice, there's a variety of what I'll call, some people call flux phases, which are these orbital antiferromagnetic phases where you have kind of these kind of loop currents which are modulated across the unit cell. There's a number of different patterns that are predicted if you can tune it towards these Van Hoff points. And the way to think about this is you can think about the charge density wave state as either having real or imaginary components. And the imaginary component is really what's driving this orbital antiferromagnetism in this material, okay? And of course, the real and imaginary components, one can either be primary or secondary to the other. So there's a rather complex space that can manifest, which makes these systems kind of interesting. A lot of different states can potentially emerge. And then the second.
Steve, one more question. How big are those? What's the size of this?
This is the unit cell level. So these loop currents are through the hexagons of the kagome lattice.
Approximately.
Oh, this unit cells like 5 angstroms in the EV plane.
So the orbital antiferromagnet means positive, negative, positive, negative.
Yeah. So they compensated, right? So there's no net moment.
Gotcha.
Yeah. All right. Okay, so I guess the second bit is that there's been a lot of beautiful work done looking at the kagome lattice Hubbard model, where if you can tune it towards this VP-type Van Hoff singularity, there's in the weak coupling limit some odd things that are predicted to occur, meaning that the on-site Coulomb interaction is predicted to be severely diminished or to vanish. And instead, the nearest neighbor Coulomb interaction can dominate and can promote attractive nearest neighbor site interactions and kind of unusual forms of superconductivity. So electron-electron mediated pairing. All right. Okay, so the first material I want to talk to you about are these so-called 1,3,5 compounds. So what the crystal structure looks like is the following. So this is a kagome net it's a perfect kagome net of vanadium ions, and each vanadium site is coordinated by antimony. And these V3sv5 blocks are then separated by these planes of alkaline metal ions, okay? And so it's a quasi two-dimensional crystal structure. And exfoliates rather readily, and it's also quasi two-dimensional electronically. And there's 3 variants that are stable in the vanadium family, which is potassium, rubidium, and cesium. Okay. If you look at the band structure of these systems, what makes them interesting is, this is kind of a band diagram along high symmetry lines. It looks kind of like a mess because it's a multi-orbital system with different atoms. But if you zoom in here, I want to try and highlight a few features, right? So if you look at the endpoint, first of all, you see there's a series of these Van Hove or saddle points, which are close to the Fermi level, okay, from this sort of DFT calculation. And these are all derived from the vanadium orbitals that comprise the kagome network, okay? So it's a kagome metal. All the states of the Fermi level, with the exception of this electron-like pocket at gamma, come from vanadium ions. Okay, and also if you're looking for kagome-like features at the K point here, you can see there's a Dirac cone. So you can start to see that there are some elements of, even sort of these sort of simple type binding type predictions of kagome band structures kind of manifest in the system, and some of the more interesting features are rather close to the Fermi level. Okay, and these systems are charge density wave superconductors. Okay, so all three compounds show a charge density wave instability at around 100 Kelvin. So the details vary depending on what the alkali site is, but it ranges between 78 Kelvin to 104 Kelvin as you change the A site. And all three systems are also superconductors, with the highest TC being about 2.5 Kelvin for the cesium compound. So, okay, the three key questions in the 135 compounds are, so first of all, what's the nature of the charge density wave state? Does this instability have any vestiges of some of the more exotic physics predicted for a kagome metal with near Van Hove fillings? What type of superconductivity manifests? With similar kind of questions, are any of the kagome physics germane to these systems? And are there other electronic instabilities realized? So for this talk, I'm going to focus on the nature of the charge density wave state. Okay, I'm happy to talk about the superconductivity if there's time in the discussion section. But okay, I want to try and get through as much as possible. All right, so the key question there is what symmetries are broken in the charge density wave phase before superconductivity forms? So it's a low temperature superconductor, but out of what state is superconductivity born? All right, so if you think about the kagome lattice, this is just looking down the C-axis of these 135 compounds. This is in the high temperature phase. And so the kagome net itself is energetically favored from DFT to either breathe into a Star of David kind distortion where it breaks up into these Star of David units, or to breathe into the so-called trihexagonal distortion where the kagome net breaks up into these hexagons and triangles. Okay, and the two distortions are related to one another. They're all 3Q distortions. Okay, with the symmetries, the distortion being the wave vector pointing to the endpoints, the three and equivalent endpoints in the brilliant zone. And the only difference between them is that the phase of one of these 3Qs can be flipped relative to the other. So basically, it's like running one distortion in reverse. Okay, so this isn't this sort of just a two-dimensional case, meaning I'm just thinking about a single layer, what's sort of energetically favored. So DFT tells you these two distortion types are rather close to one another. But these are three-dimensional systems, and so if you start to think about the interlayer correlations, you can have a three-dimensional charge density wave state where you can, for instance, stagger the distortion of one plane relative to the other, meaning like if I have a trihexagonal distortion in one layer, I can shift it by half a unit cell relative to the next layer, and I can end up with a three-dimensional charge density wave state. Or you can imagine staggering the distortion types, it's trihexagonal, Star of David, for instance. You can generate some sort of three-dimensional structure by mixing in a distortion mode with this L-point symmetry. Okay, and so, the charge density wave states that result in all three compounds are shown here. So the vanadium, so the potassium and the rubidium 135 systems, they both form a 2x2x2 supercell, okay? And they form the so-called staggered trihexagonal distortion. So in an individual layer, more or less C6 rotational symmetry is preserved, but one layer is shifted relative to the other by half a unit cell, so you end up with an orthorhombic unit cell, okay? In the cesium system, the charge density wave state seems to be much more complicated. Now, this is what the average structure is. There's this local structure in there that I'm happy to discuss if anyone's quite interested in details, but it has a larger supercell in the average sense. And it seems to be comprised of a mixture of both Star of David and trihexagonal distortion types. All right.
All of them are sensual symmetry? Sensual symmetry.
Yes. Okay, so, all right, so that's sort of the standard real part of the charge density wave order. So what's going on in terms of perhaps an imaginary component or predictions of realizing this orbital antiferromagnetic state? And so what makes the charge density wave state interesting is that there's sort of hints of time reversal symmetry being broken in the CDW state from a variety of different probes. With the initial hints being STM studies, where basically by looking at the STM Fourier transform of the charge ordered state, it seemed to respond to the application of a magnetic field. USR seems to see some uptick or a change in the muon spin relaxation rate upon entering the CDW state. There's hints in magnetotransport of either inversion symmetry being broken or time reversal symmetry being broken. There's a large anomalous Hall effect with no spontaneous component. So okay, whatever we want to call that. Yeah.
Anomalous.
Okay, anomalous, a weird Hall effect. Yeah.
Sorry, how does the torque magnetometry tell you about the time reversal symmetry breaking? Is that like an implied nematicity?
Yeah, I think in this case it's an implied nematicity, but yes. Okay, so I'd say, but two of the more striking observations is there was a polar Kerr effect, which from this group, which is in Kyoto, I believe, where they claim that as you cool into the charge density wave state, they see the onset of a polar Kerr signal that can be switched with the application of a magnetic field. And also a scanning circular dichorism measurement done by Liang Wu's group at the University of Pennsylvania, where they see these sort of subdomain structures. So within the structural domains, they see different domain structures with opposite signs of circular dichorism form below the CDW state in all three compounds. Okay, and okay, but these are hints, but one of the issues is there's always issues with these, it's a subtle effect for a lot of these things. And I would say that the most striking issue really is there's some experiments that have been repeated on nominally the same sample by different groups, and they see different things. Okay, and so the polar Kerr effect, for instance, this is work by Aaron Kapeltunik's group, where they don't see the effect on nominally the same compound. In STM studies, there are STM groups that claim to be able to not be able to repeat the original STM reports of being able to switch the CDW state with an applied magnetic field. There's issues with interpreting magnetochiral transport. There's some caveats with some things. Like as we mentioned earlier, there's no spontaneous Hall component in these materials. And in the USR studies, I'll just say that the effect is subtle, right? So the actual average fields that the muon's seeing are on the order of the nuclear moment, okay? So these aren't really strong electronic moments that are being sampled by muon. So again, there's a lot of this is sort of open to debate still, but there are hints there, and I would say this type of measurement, contradicting, this circular dichorism and this other polar Kerr measurement is very striking, right? I mean,
The temperature is very different, 130 K.
here for the torque, yeah, this is something very new. I don't know where this is coming from. It's something strange.
So just to clarify, Kerr effect will not see antiferromagnetism,
That's
correct?
It can see Q equals 0 antiferromagnetism in certain cases.
Okay.
So basically, if you have a multi-site unit cell with two magnetic sites and it in the magnetic order doesn't enlarge the unit cell, you can see that in some cases, right? Like ultramagnets are an example.
Is it known that we can alter magnetism with Kerr effect? Is there any measurement?
Yeah, I was talking to, I think yes, from a while ago, they weren't called ultramagnets, but there are classes of antiferromagnets where Kerr effect is known to occur. Peter Armitage told me a bunch of them recently, and I can't remember them now, but I'll try and remember.
There's manganese tellurium and some oxides and,
No Kerr effect as much.
well, nothing really has been done on ultramagnets experimentally, but they're supposed to have chiral fermions. And so anything that can detect that will probably register.
Since we're asking about all these things, can we, on the MUSR, the relaxation rate went up for some and down at different fields? Do you understand that? Or?
No.
Okay. I know you're not a MUSR person. Okay.
And this is under field, right? Zero field MUSR also shows an effect. But yeah, no, this change as an applied field strength is not obvious what's going on. Yeah. Okay, but I will say something that's been interesting that's very recent. Some of the work is, Vidya has some recent beautiful work looking at the rubidium compound, okay? where they were able to reproduce this sort of magnetic field switchable charge density wave state from the original report from Hassan's group at Princeton. But they also were able to resolve a piezomagnetic response in the system. Okay, and so the interpretation here. Oh, okay, and I guess a key observation is they can also switch the chirality apparent on the surface of the CDW by the application of a linear electric field, meaning like a linearly polarized light can switch it. And so I think one of the takeaways here is that sample strain can have a profound effect on altering what different groups see via uncontrolled strain effects. And this has been shown actually in a very complementary work by Philip Mull's group. What they did was they took a material, so I think they took the cesium vanadium 325 system, and they cooled it down and they measured in-plane transport anisotropy. And they saw there was a well-defined temperature below which an apparent pneumatic term turns on, okay? So like you have in-plane anisotropy turn on below, say, 35 Kelvin roughly. But then they encapsulated the crystal in glue to remove strain and they made some device and they basically carefully removed the strain as much as they could. And that term went away. Okay, so basically the anisotropy goes away when they look at the in-plane transport. But then if they look at that sort of strain-free crystal and they apply an out-of-plane magnetic field, they can see that it comes back. So this kind of, to me, implies that there is a piezomagnetic term, and that means that, I guess the most straightforward thing is that there is maybe some subtle time reversal symmetry breaking in the CDW state. But okay, this is a conjecture at the moment, but I think that might unify these two observations and also explain why there's such variance in the literature because of this sort of uncontrolled strain effect. So hopefully this gives us some guideposts moving forward on how to look at these materials.
Do you know what the jumps are in the field? All the jumps in the field, do you know what they are?
I'm assuming that's some type of like
Like
quantum
oscillations?
oscillations. Yeah.
Yeah, maybe.
They're fairly high mobility metals, so like even my group can measure quantum oscillations.
Well, why wouldn't you see them in the blue data?
Oh, this is some difference, some ratio, I guess. I don't know. Maybe they stayed the same, so they always normalized to one. I don't know. All right. So one thing we can do is we can just say, okay, let's take a look at a crystal, a nominally strain-free crystal, and we can just look at with dark field X-ray microscopy. This is work done with Zahir Islam at Argonne at the Advanced Light Source. And all I want to show you is this is basically just looking at a real space image of strain in a sample. And so you can see these hot spots here, the strain is larger than these cold spots here. So there's sort of these ribbons of strain that exist in most real materials, okay? But in these systems, they're particularly soft metals. And so you have strain fields that are sort of baked into the system that people, I think, we need to start learning how to control. Okay, so I'm going to summarize the charge density wave state of these materials and potentially why it's interesting is you start with the sort of kagome net. You have a real component, this 3Q distortion that can either go into a trihexagonal or Star of David state. Each of these can carry with them a potential imaginary component, which would carry this orbital flux phase, which is the potential orbital antiferromagnetism that breaks time reversal and maybe drives some of the more anomalous properties. And of course, each of these can have an out-of-plane component, right? So you can have some modulation, a staggered trihexagonal modulation of the potassium and rubidium variants, or some larger unit cell that staggers between Star of David and trihexagonal mixed with this staggered trihexagonal state in the cesium compound. All right, that's just kind of capturing what might be going on. Okay, so then we can ask questions. Okay, so now as you cool from the charge density wave state down to the superconducting state, is there anything weird that goes on, or is it just simple one phase transition to another? And so, the answer is something rather complicated seems to be happening, and I don't have a good answer for exactly what's going on, except to show you this is experimental phenomenology that shows you that there seems to be some crossover points in the material as you cool from the onset of charge density wave order all the way down to the superconducting state. And so this is just sort of capturing some of the stuff. So you start with charge density wave state where potentially you have some onset of time reversal symmetry breaking, depending on which probes are looking at it. And then there's a sort of an intermediate temperature scale around 60 Kelvin or so, where sort of short lifetime lattice modes turn on, as seen via optical measurements. At the same time, sort of charge stripes are pinned at the surface, as seen via STM measurements. Raman sees lattice anomalies at this same type of sort of intermediate temperature scale. And as you continue cooling down, then there's sort of another temperature scale that seems to reflect more of what's going on in the electronic sector, where around 35 Kelvin, there's sort of 1D quasi-particles appear on STM measurements, looking at their quasi-particle interference spectra. This is where the sort of chiral or time reversal symmetry type features are seen in transport. This is also where in strain crystals, it seems, a nematic type of fit state turns on. And then as you cool further down, you enter the superconducting phase, and then there are claims of sort of a pair density wave-like anomaly in the superconducting state. And so, but if you just look at if you ignore all this stuff in the intermediate and you ask what type of charge correlations are sitting down at low temperature, really the probe that has explored this the best are STM measurements. And if you look at what STM sees in the low temperature state in the superconducting phase, they see 3 separate charge wave vectors. So the first is what they call this 3Q2I0. That's just the charge density wave state I told you about. This is the staggered trihexagonal or the 2x2 enlargement of the unit cell. Okay. They also see this coexistence of these, what they call 1Q4A0. That's these charge stripes that are at least pinned at the surface, seen in STM. But then at low temperature, and I think the onset temperature here hasn't been carefully experimentally defined, there's an additional wave vector which is called 3Q4A0 over 3. And so if I look at the Fourier transform of what they see on the surface in terms of charge correlations, what they see basically are these are the 1D 4A0 type of correlations. These are the 2x2 correlations. And then there's this intermediate sort of 4/3 A0 correlations. It's okay. The one, and along this wave vector, they also in the superconducting state, the superfluid density seems to be modulated along this wave vector. And it's another 3Q order. So one proposal is by Zikang Wang's group, is that potentially this additional wave vector emerges due to a staging of electronic order. Basically, you start in the high temperature state where you have these nested Van Hove points. Basically, you enter the charge density wave state, and then basically you fold the units, you fold the Brillouin zone, and you end up with what they call churn pockets that are also nested. Okay, and at a lower temperature, that kind of new nesting wave vector drives a secondary order parameter. This is sort of still ongoing to figure out what's the origin of these, but it seems to be quite a rich spectrum at low temperature in these systems. Okay. Yeah.
Steve, this has nothing to do with the pair density wave.
Well, I think that's the wave vector they claim the pair density wave.
I see, but that's being seen above the superconductivity C now.
Yes, I think they claim in the paper that it's around 4 Kelvin or something, but I haven't seen a really thorough explanation of where it turns on.
Oh, above TC?
I thought they claimed it's above TC, yeah.
What is it about this material that makes the properties so rich?
Well, confusing.
Yes.
It's very confusing, yeah. I'm just gonna confuse you more because it's even weirder when you start, I think it's certainly a large component has to do with the fact that you have multiple Van Hove points here, okay, near the Fermi level. And which one happens to be dominant at a given temperature is probably driving the physics, but also I think there's an interplay with this antimony PZ pocket that's rather unaccounted for in a lot of theoretical models that seems to play a large role. Okay, so since there's, yeah.
One question. So vanadium is Sol plus?
It's, this is really covalent system, so ascribing,
I see.
there's no local moment on the vanadium, right? So it's just basically polyparamagnet. Okay, if you want to do valence counting, then you would say that there's 1 electron per 3 vanadium ions. If you want to say it's an ionic system.
The orbital would be just one ampere electron. Okay, shared by 3. Okay.
Yeah, but it's not really that.
Oh.
But okay, but it's useful to think of this way sometimes. Okay. So there's a lot of materials talk, so I get to talk about what we do with brute force because I can't do these STM measurements that Vidya does, but we can definitely tune the filling by doping electrons or holes in the system, and then we can ask what happens to the charge correlations to the instabilities of the system as we tune the Fermi level about sort of these supposedly important features, coming from the kagome net. Okay, so one, I would say the most interesting example of this is that you can hole dope the cesium compound, and when you do so, 2 kind of interesting or unexpected things occur. The first is that the charge density wave order collapses really fast. This is a square root scale, sorry, my students get creative with how to represent data. But But so basically it comes down rapidly in around 5% holes per formula unit. You have sort of this first order disappearance of the thermodynamic anomaly associated with charge density wave order. Before it disappears, the TC peaks in the charge density wave state and then goes down sort of near the terminus of this CDW state. And then it comes back and you have sort of a second dome out here at higher hole doping. Okay, so that's kind of an unconventional behavior. It's not a simple trade-off between the two states. And then what we can say is, okay, what happens to the charge correlations as you move across this phase diagram? Okay, if we're exploring competing instabilities that can be realized in the kagome band structure, what do the charge correlations do? Okay, so we can look at the peak of this first dome here in the charge density wave state, and if we look at X-ray scattering, this is the HK plane, so this is the AB plane of the kagome net. These peaks here are at superlattice positions that correspond to the 2x2 charge density wave order of the parent system, okay? So more or less in plane, the physics doesn't change from the parent compound to here. The charge correlations become a little more quasi-two-dimensional between the planes, but that's the main qualitative difference. But if you move here to sort of this, to a point in which this, the CDW phase has nominally vanished, and ask what do the charge correlations do there? So here is what you see. These are qualitatively different than here. And if you fit this in a three-domain model, then effectively what you're looking at, again in the HK plane, is you're looking at incommensurate quasi-one-dimensional charge correlations, okay? That, in three different domains of those, okay? So there seems to be a proximity of sort of a quasi-one-dimensional charge instability. And we can actually keep doping, and we can look out here at the peak of the second dome, and out here it even gets weirder because here you still have broken translational symmetry, you have an incommensurate cube. But here, you basically restore translational symmetry, but you still have these sort of quasi-one-dimensional domains. So rotational symmetry is broken here, but it seems like translational symmetry is restored. So, you might call this a nomadic phase, potentially. And then if you keep going out here, where superconductivity dies, then all the charge correlations kind of are gone within the resolution of our current measurement. Okay, so I don't have an answer for why this happens, but it's certainly a rather unconventional charge landscape that seems to be realized, in this, due to this particular band structure. All right. Okay, so that's the 135 system. So one thing you can do is, okay, since there are a lot of kagome structures that form in nature, we can try and find another one that maybe has a similar band filling and see if we can realize similar phenomena. A promising one are these so-called 166 compounds. And so it's a rare earth ion, vanadium 6-tin-6. So it has the same type of vanadium kagome net, but in this case, it's coordinated by tin. And then you have a rare earth layer, a triangular lattice of rare earth ions that sits also in the lattice, okay? Okay, so this is kind of appealing because the 135 systems, one of the features is the vanadium-based kagome net is non-magnetic, so you can avoid magnetic instabilities. In this thing, you can actually perhaps reintroduce magnetism or collective magnetic order to interface with instabilities realized in the vanadium-based kagome net. All right. This is what the band structure looks like for a non-magnetic variant, so the yttrium vanadium 6-tin-6. Okay, and so if you look here at the M point, again, you see there's a series of these Van Hoff points coming from the vanadium ions, okay? You can see that there's Dirac points that are now sort of at the Fermi level, okay? And there's sort of a flat band feature up here, far away from the Fermi level. But one key difference is you don't have this antimony, you don't have this electron-like pocket coming from tin, like in the 135 system. So it's a little bit different. But in terms of the kagome physics, these Van Hoff points are very close to EF. We've done some work, trying to say, well, okay, what kind of magnetic states can you engineer in these systems? You can put terbium, it's a strong uniaxial ferromagnet that you can start to interface with these kagome-based vanadium D states. You can put, other reports have shown you can put erbium or thulium, you get an easy plane antiferromagnetic order. So you can really play with the magnetic states that you realize. And as is the case most time, if you put the most isotropic rare earth ion, so gadolinium, then you can get some incommensurate complicated multi-Q order, which is, we're still sort of exploring this. It's not fully defined whether or not it's amplitude modulated or like a spiral state in that system. Okay. But there's some work that said, okay, instead of taking yttrium, David Manders' group put scandium, which is a much smaller ion than yttrium in the lattice. And when they did that, and they looked at the magnetization and resistivity and heat capacity, there's a phase transition that appeared, okay? And it appeared around 100 Kelvin. And the superstructure that formed went from the parent 166 structure to a root 3 by root 3 by 3 enlargement, okay? And so the Q vector ascribed to this is a third, a third, a third. And the question is, okay, is this physics at all mappable to the charge density wave state in the 135 system, okay? And I'll show you, I don't think it is, but it gives you, but I think the takeaway is going to be this type of structure and this particular variant actually gives you a pathway to maybe a different type of charge order.
Steve?
Yeah.
There's no superconductivity in these?
No. Yep. Good question. Yes, that's right. James is posting tomorrow. Okay. Okay, so so what's going on with the charge order in this system? And so if you look at the DFT, what are the energy, DFT predicted instabilities of this lattice. And so this is some work by Binghai Yan's group. And so DFT predicts that the most energetically favored distortion is not the experimentally realized root 3 by root 3 by 3, but instead it's this root 3 by root 3 by 2, okay? So the same type of in-plane periodicity, but a shorter modulation along the c-axis. And the question is, why the discrepancy, right? So, okay, and is the discrepancy interesting? Okay, so I'll try and motivate that I think it is interesting. And so, okay, to try and motivate why I think it's interesting, first let me just maybe take a, okay, I'm doing it right on time, right?
Yeah,
Okay.
5 minutes.
All right, okay. Okay, so the first is to think about the structure. Okay, so the 166 structure, which is this, you can imagine as a kind of a variant of this 1-1 structure. Okay, so Joe talked about this iron tin structure, right, which is this binary. And he mentioned that, okay, to stabilize the kagome net, you need to put an atom in the center of the void, right, in these binary compounds, right? So then you have these tin atoms, for instance, sitting, if there was a vanadium tin compound, they would be sitting there, okay? But then what you can imagine is, okay, I'm gonna take this iron tin structure, I'm gonna add a rare earth ion, and where's it gonna go? So it will try, in this layer, this tin 2 layer, that's a honeycomb lattice. It's gonna try and sit in the center of the honeycombs, okay? And when it does that, it's gonna push the tin atoms above and below it away from it, just sterically, okay? And so that means that this distance gets compressed, and then this distance gets expanded, right? And so then you can only do this every other layer, and when you do that, you get this 166 structure, okay? You get effectively a bilayer lattice. Okay. And so if you look at what's actually going on in the charge order phase, the atoms that are moving are not really the vanadium atoms. They move a little bit, but the main actors are these tin and scandium ions, okay? And they're moving along the c-axis, okay? And so one way of thinking about what the primary distortion mode is that if you think about the yttrium vanadium 6-tin-6 compound that I showed you originally, if you look along, if you look along the c-axis, so looking along these, what I'll call these scandium tin chains or these yttrium tin chains along the c-axis, these guys thread through the these chains thread through the honeycomb or the hexagons in the kagome network. All right. So in the yttrium system, the distance between tin and yttrium is about a third of the c-axis, and it's the same along the whole chain. But once you put scandium in, which is a smaller atom, basically you allow for an instability in which the tin atoms can move in closer, okay, to the scandium ion, okay? But as they do so, right, so now this is adding in the hexagons from the vanadium-based kagome network. When this tin atom tries to move towards the scandium, or this tin atom tries to move the scandium, they have to kind of move closer to this vanadium hexagon, and there'll be a steric effect or an energy penalty for that, right? And so what they'll try and do then is they'll try and basically, one of these, what I'll call trimers, will try and move up, and the other one will try and move down relative to each other to try and minimize their energy. This is like a heuristic model of what's going on. okay? But the lattice connecting the centers of the hexagons of a kagome network is a triangular lattice, right? And so that's a frustrated lattice, right? So if you just try and decorate it with one of these guys moving up, one of these guys moving down, then you'll have some, in principle, if you map this to some Ising degree of freedom within the chain, you'll have some residual entropy, and the lattice won't like that. But it can unlock an additional degree of freedom by just modulating further along the c-axis, where you have one of these trimers moves up, one moves down, and one doesn't move at all. Okay, so then you can decorate this as an ABC kind of three-state POTS type of model. And indeed, this is the experimentally realized ground state. Okay, so fine. So what's the relevance of this at all, right? So the answer is that if you look with X-ray scattering, the charge density or the charge order transition of this compound is at 90 Kelvin. But if I look at a wave vector that corresponds to this periodicity, so a third, a half, okay? So I look at a wave vector corresponding to this, what I'll call frustrated type of order. There's extensive charge correlations that are present even at room temperature, okay? And so if you look, what happens is you cool down, these charge correlations get more and more intense. You have three-dimensional first order transition to three-dimensional long-range charge order, but these charge correlations still sort of stick around and dampen as you cool through. So these sort of residual correlations are the primary energy scale in the system. They're up present at high temperature. They just can't simply, they're sort of frustrated from driving long-range order until you can sort of unlock this additional degree of freedom along the chain. And one can look at this a bit more. So this is looking at a third plane. You can see these sharp Bragg peaks, right? These are for the long-range charge order. You can see this diffuse scattering cutting through. That's just from these short-range correlations of a third, a half wave vectors. We can watch the correlation length sort of diverge along the c-axis, along this diffuse scattering, a third, a half. It diverges, it hits about 3 unit cells, and then it crashes down, and you have this sharp onset of long-range charge order. So it's kind of an interesting example of this like one-dimensional instability along the c-axis is sort of frustrated from forming due to the frustration is mediated via the vanadium-based network. Okay, so if you want to kind of test it using materials, we can alloy the system a little bit. So you can place a little bit of scandium with a little bit of yttrium, which is bigger, and you can introduce disorder then along these chains. And if it's a 1D instability, it should be extremely sensitive to disorder. And indeed, charge order is completely suppressed by the time you put 7% yttrium onto the scandium sites. Okay, and that's just a susceptibility showing you charge order is present in the parent, damped by 3% and gone by 8%. We can do X-ray scattering and show that more directly. And one can show here at the 3% sample, you have only these third, a half short-range correlations that survive. There's no more long-range charge order. And then at the 8% sample, all charge correlations have vanished. Okay. And I'll just finish by saying, okay, there's other people who are looking at the same time. Seems like everybody started studying this material at the same time with the consistent results across these different results. So this is other diffuse scattering work, and this is by Santi Blanco. This is by Jinhao Chu at University of Washington, and there's also some other diffuse scattering results coming from the USOM's group. And yeah, there's also been impurity substitution work that's been done recently also by David Manders's group. And so with that, I'll just finish and maybe allow for some discussion, is that, okay, we think that there's new classes of kagome metals, as Joe mentioned in the beginning of the talk, of the conference, with flat bands that are promising platforms, but also looking at fillings near these Van Hove points that also can drive seemingly complicated or very interesting electronic states. The 135 class of vanadium-based compounds seems to show a charge density wave state that's very complicated with hints of time reversal symmetry breaking. The onset of charge density wave order relies on these saddle points being near the Fermi level, but it also probably relies on these antimony states being at the gamma point. And yeah, there's other interesting classes of vanadium-based compounds. For instance, this 166 series shows sort of like a different flavor of charge instability. So I think the phase space is large for these materials. And with that, I'll thank you very much for your attention.
Very interesting. Can you find your earlier slide showing flux state? Flux, each layer, different kinds of a flux state?
Oh,
Yeah,
okay.
Very early on. The question I have is, so far, what is kind of a best evidence for the presence of this flux state, as well as orbital magnetism so far? And then for the future, what is the kind of best way to really confirm this? Especially I'm interested, you have this yellow, this hexagons, whether they are, each layer, whether they are kind of ferro-type orbital or anti-ferro-type orbital, what is the kind of best way to see these things?
Yeah, I think in an ideal case, like neutron scattering would be great. But you need a momentum resolved probe that could couple to time reversal symmetry breaking. And there's some technical challenges with neutrons that have to do with the samples themselves, the sample size themselves, but also with the moment size. So the moments, if this state is present, the moment is certainly very weak, and it's potentially just beyond the resolution of standard neutron diffraction, let alone polarized neutron diffraction, which you would really want. So potentially resonant X-ray scattering, like on the vanadium edge, could be done. It may require some creative thought. I mean, I haven't thought about whether or not you can actually reach the right Q vector with the vanadium L-edge resonance. So there might be some ways of doing it with resonant scattering. I think that's probably the most promising for a momentum resolved probe. I think in terms of the strongest evidence that something weird is going on, I would say the STM evidence is, it's hard to get around that the charge density wave state is coupling to a magnetic field, in which case you would have to say that it's, at least I don't know of another way of doing it without breaking time reversal symmetry.
So with magnetic field, what really happens in STM?
Yeah, so, well, okay, Vidya can correct me if I'm wrong, but what they do is they, you basically survey a surface, and then they Fourier transform it, and they see the charge superlattice peaks, okay? And those are along 3 different Qs, which are nominally, they can be inequivalent. And so they see inequivalent spectral weight at the 3 different Qs.
Oh, boy.
Okay, but they can flip the winding of that with the application of a magnetic field.
Yeah, so maybe if I allowed to comment this, if there's enough time. So, I don't know nothing about the STM, but when you have 6 peaks, because of Fourier transform nature, plus K minus K intensity has to be identical, okay? Plus K, this point and that point has to be identical. When you have 6 peaks, so that means you have only 3 peaks left in terms of intensity, what you can do. Then the only way you can do is either 1, 2, 3, or the other way 1, 2, 3. That's the only way you can do. So what it means is if there is any way you break perfect C3 or C6 symmetry, if through some kind of anisotropy, some kind of sample tilting, you always get difference between 1, 2, 3. Peak intensity will be different. That's nothing to do with chirality. That's nothing to do with chirality. So, and then with magnetic field, sample can move, and then this two.
Well, STM in principle is looking at the same.
There are all these complications. So I just want to warn this.
Okay.
Son, I have lots of stuff to say about this, but I think I can tell you later. Because we can talk later.
Steve, can you just?
I can tell you I understand exactly what you're saying, and I can tell you why.
I love to hear. I love to hear. Yes.
Okay, and so what I will say, even though this data is directly at odds with this data, I'll say that, okay? But if you look at this data by Liang Wu, okay, they do 2 types of measurements. So they survey around the surface, and they do Kerr rotation, and they do circular dichroism. Okay, all right, so the Kerr rotation, the system, when it goes to the CDW state, it breaks 6-fold rotational symmetry, and it should form 3 domains, okay? And they can see those 3 domains formed by each with principal axis rotated 120 degrees, okay? But within those domains, they see 2 different types of circular dichroism domains, subdomains form, with different signs. And they can field polarize those.
So they apply magnetic field?
They can apply a magnetic field, yeah.
They can see one domain each region. Actually, there should be, entire region should be 1 domain.
Okay.
No, not necessarily.
No,
not necessarily, because strain is the problem in these.
No, but still, there can be disordered the region.
Strain,
However, domain has to be 1 domain.
If you have enough strain, it pins the it doesn't allow
They're
this.
taking dirty vision, that's true.
So,
No,
okay,
it's not dirty, it's just strain is so, sample is so sensitive to strain that if you have strains, it'll prevent this whole thing from
Well, it
rotating.
depends on how largely the field you apply all these things.
so I don't want to, okay, so I won't talk about the magnetic field aspect of this because I think the picture may have evolved since then and it's not published, but okay. And so I guess the one measurement that's not in principle like quasi-surface or surface sensitive is the MUSR data, and I think the MUSR people really believe it, okay, but it's a little, it's an open question about what they're really seeing.
What really bothers me is Aaron Capitone always sees, his signal, and he sees nothing. That scares me.
But when Leon heard that meant he believed it.
Can I interrupt the Madhavan Sang Chong discussion, because they're going to discuss this afterwards.
Yes,
I'd like to ask a different question.
Yeah, okay.
As you know, circular kind of current patterns like this have been interested theorists in other contexts, and one famous example where it may or may not have ever occurred is in the cuprates. Do you ever see any strange metal behavior in the transport, in the approach to the formation of this state? Do you see any unusual transport? It is a metal after all, so.
No, there's not a strange metal state in the vanadium-based 135s that we've seen.
No sign of the circulating currents producing odd, unusual scattering processes as they become critical or whatever.
Not that I'm aware of.
I see.
Yeah, not that I'm aware of. There's a titanium-based system, like a cesium, like titanium 3bismuth 5, that doesn't show long-range charge density wave order. But there's claims that there's some rotational symmetry broken, like an electronic pneumatic phase in that. And in that system, there might be some strange metal behavior, but that hasn't really been
And
fully
is there any hope for being able to squeeze the TC to zero
on these.
in these, or do something that tunes it to zero, make it go quantum critical?
Well, he did it by doping. You had the doping phase diagram, right?
Yeah, that's the by doping. Yeah, you can suppress TC only in the cesium compound. Yeah, sorry. So in this system, right, there might be some area here that one could try and thread in here if you could get doping homogeneity good enough. Maybe there's some deeper minimum here.
I see.
Yeah.
Okay, thank you.
I had a related question about the 166s. You had a doping dependence, but it didn't look like the transition got suppressed.
It's still up.
Temperature, it just got ruled out at constant temperature.
It goes down a little bit, yeah, but that's right. It's a first order, really sharp thing, right? So what you're seeing is really this first order locking into these correlations that are always present at higher temperatures. Why those correlations vanish once the long range order is gone at 8%, not 100% sure. I don't know if it's a signal noise thing to the X-ray data or not. But you're right, it goes down, it kind of blurs out. It's not like a systematic.
8% is a lot of disorder. It's, it's like 1
In-
it's
Yes.
something different.
Yeah.
So every 2
In the sodium cobaltates, we have no superconductivity. So we could be near a critical point. We could be in that situation. But of course, the sodium cobaltate, we have the flat band. While here, you are far from the flat band.
Yeah. Okay.
So for the second material that you were discussing, 166, there's a is it a 3D Dirac cone or is it a quasi 2D Dirac
It
cone?
should be 3D, yeah. I think in the 166, there's quite a lot of dispersion along KZ. They're much more three-dimensional.
I was curious because the material breaks time reversals.
The 166, there's some reports of that. I don't know what to make of them.
But the moments are not ordered.
So, okay, in my opinion, I for the 166 compound, there's a report from USR where they claim to see a similar signal as seen in the 135 compound. But there's no local moment in that system. If you look, it just looks like non-magnetic. There's also a report of a similar anomalous Hall type of response. But I think that's where the comparison's at.
Yeah.
A great talk. How do we know that instability is driven by one hole singularity or like chiral distortion?
Okay, so the Van Hove question, it's a good question. If you, so I think the current arguments now are, if you look at photo emission and you ask what bands care about the onset of the CDW, it's the Van Hove, it's the P-type Van Hove that gets gapped below CW. The rest of the states don't really care.
Got it. Okay.
So I guess, okay, naively, that's involved in the CDW and important for it.
I see.
Yeah,
Maybe
but
the thing is we couldn't tune the Fermi level just there, right? Or maybe
yeah, and so I think then they sort of tune the Fermi level. Okay, I might be. There's some other studies where they dope titanium instead of tin,
okay.
and titanium adds holes similar to what we did. And I think they tracked it, and once the Van Hove, they sort of correlated. Once the Van Hove pushes above Fermi level, they lose the CW.
Thank you.
Yep. In your substitution where you see the onset of these two kind of distinct superconducting domes, go back to
Yes, sorry, I'll go back. Yeah.
So is there any composition where you see two TCs, or it's always, or those are all two TCs? Sorry, maybe I'm confused.
So is there a composition, like if I look at here, do I see two different onset TCs?
Right, yeah.
Like in magnetization or something?
Right, I'm thinking of something like telluride where there's.
Oh, like heat capacity or something like that.
Yeah.
We haven't looked at that. I haven't looked in that level of detail. That's a good question.
Okay.
It's actually, yeah, we're sort of still kind of struggling to get precise dialing in, getting crystals across this phase diagram. And the crystals are not easy. Right? Yeah.
Can I ask a question about this piezo? I guess there's some suspicion of piezomagnetism. And how much in the experiments is controlled in terms of the direction of strain, or known about the direction of strain in these materials? Or is that still pretty much, like, have there been any controlled strain experiments, I guess, maybe?
Yeah, so I think, so people have applied, this is what's weird, okay? So naively you would apply in-plane strain and you would want to bias, you would think that CDW temperature would shift, TC would shift or whatever, and that effect seems to be reasonably weak. And mainly driven, in fact, just via the Poisson ratio, it's mainly the C-axis response that really drives down the CDW.
So the people haven't done hydrostatic strain.
People have done hydrostatic pressure, and basically the CDW collapses quickly, and eventually another superconducting phase forms. But at that point, the C-axis collapsed by 20%, something like this. So it's very anisotropic. The stuff that Philip did is removing very small residual strain fields that gave rise to a very subtle transport anisotropy. So what's driving that is sort of an open question.
I think so far you are discussing the CW is from electronic view, but I think there are also some reports that say that there is electron phonon coupling and there's some changing in the phonons. So what's your opinion on this?
I mean, I think every CDW system this debate rages on, and they all have electron phonon coupling, yes. To distort the lattice, you need electron phonon coupling, so yes, that's happening, yeah. But you need both. So it's not as simple as one or just the other.
Question here.
Yeah, very nice stuff. So, do you care to say anything about superconductivity? Is there any updates or any further understanding of the superconducting state itself?
Here's my, I'll try and capture it. I tried to distill it down because you could spend a whole talk just talking about superconductivity. Oh yeah, okay, I ran out of time to talk. Wait, hold on. First of all, these people did all the work, sorry. Brendan Ortiz is now at Oak Ridge National Lab. He discovered this series of compounds and he really spearheaded a lot of the initial materials work in our group. Ganesh has been doing all the 166 work I showed you. He also has worked a lot on the 135 compounds. Linus, Andrea, and Jaden did a lot of the scattering and follow-on work, and Parnaz has done a lot of the DFT work on this. Yeah, sorry, that's my fault. And then we've also had many different collaborators collect a lot of the data I showed. And then there's this is one of the fun things about condensed matter. You can have a large team kind of organically driven. Right? Okay, that being said, okay, here's all right. So I'm going to distill it down. It's a clean limit superconductor, highly anisotropic. HC2. The anisotropy is about a factor of 9. It's certainly 2 gap. as you know, JP, like one gap is small, the other gap is large. It's singlet pairing from this Hubble-Schlichter peak that's been seen by NMR. So I think two gap models are the kind of predominant.
So the two gap data is from STM or?
This is from soft point context, but I think also penetration depth, peak capacity, lots of probes that sort of
Just fitting, okay.
with two gap. This is some beautiful work by Fungi et al. And Shibuchi here, where penetration depth using irradiation damage. In the sort of disorder-free limit, they basically fit with one anisotropic gap, but fully gapped, and one isotropic gap. And so from this study, because of the resilience for disorder, you could suggestions that maybe you could exclude sign changing gap functions, so maybe an S++ is the most likely. There's sort of two open questions. One, I'd say there's some recent theoretical work by Brian Anderson that shows that basically, when you think about a kagome lattice in particular, it's sort of generic arguments for disorder being strongly pair breaking for sign changing order parameters versus non-sign changing can maybe not be true due to this sort of sublattice selective scattering that comes with the details of the kagome lattice. So maybe that's still an open question in terms of whether or not it's S++, S plus minus, or D plus ID. There's this other odd thing. This is from MUSR again. In the CDW state, because this is the rubidium 135 system, okay? When they do their MUSR thing, they cool down, and when you enter the CDW state, they see muon relaxation do something weird, okay? Okay, and then they keep cooling down, and okay, fine. But then they apply pressure, and they can suppress the CDW order parameter. And then when they cool down, they don't see anything happen in this kind of funny change in the muon spin relaxation rate until they cool below TC in zero field. And so that's kind of odd. So from this, they're claiming that maybe there's some time reversal symmetry broken below TC. So if that's true, then maybe D plus ID. I don't know. So it's open questions, but that's sort of speculation.
And there's nothing to suggest that the nature of the superconductivity changes across the tin.
I think currently no.
But if that's with pressure, are you suggesting that the same thing happens with doping? This one, this.
Yeah, whether or not the exact same thing is happening, I don't know.
Yeah.
Sorry, I didn't quite follow what special property of the kagome lattice means that disorder won't break sign changing order parameters.
All right. So I tried digesting this paper. I think it has to do with the phase space that you can scatter to because the wave function sort of localized on one site. And so evidently, I don't know, I guess when they calculated it, they basically said that all disorder is sort of equivalently pair breaking for all singlet states. The same argument didn't apply to triplet states, for instance. But yeah, here's the reference. Sorry.
Yeah. So they're just saying that in the absence of strong pair breaking effect, it could possibly be measured.
Yeah. That's,
Right. Well, let's thank Stephen for this.